Hello all, welcome to my course on methods of adhesion measurement, theory and practice. We are discussing about contact mechanics, and we are last lectures we discussed about loading on an elastic half space. In the last lecture we talked about axi-symmetric loading. So, we will continue this discussion today, and in the last lecture we discussed about distributed uniform load on an circular area of contact, and there if you remember we obtained the vertical displacement V at the surface, that is g is equal to 0. So, we already obtained this quantity at different location as a function of r because of this uniform load, that is P is equal to P0 over here. So, today we will start discussing about the horizontal displacement. So, here there is a small area at this point C, and this area is given as S ds into d phi. Because of the load on this area, what is the horizontal displacement at here? Now, remember that this displacement, horizontal displacement along the r direction, I mean radial direction. So, it is actually in this direction. So, infinitesimal displacement will be in this direction. So, in order to find out that what will be the net displacement along this direction, we need to take the cos component of this, and the sine component will cancel each other over integration throughout the area. So, we need to worry only about the cos component over here. So, over here we have this P is the constant. So, basically P0 you can write or whatever is constant, and this is S gets cancelled over here, and we need to multiply it with cos phi in order to get the horizontal displacement u along the in the direction of r, and we will get here something like this over here, and we integrate it with respect to s and phi the way we did it for the other case. So, for vertical displacement. So, let us say for given phi, and this s varies from s1 to s2 over here, and here p is constant. So, here we will get it 1 minus 2 sigma 1 plus sigma by 2 pi e, and this is p here, and this is s2 minus s1. So, s2 minus s1 we had obtained in the last lecture. So, finally, it will come out to be something like this. So, here actually integration now here the integration is phi is varying from 0 to 2 pi. So, we need to take only s1. So, therefore, it is 0 to s1, not s2 minus s1, but 0 to s1, and the s1 is given by this expression. So, over here like that. Now, we need to find the integration of that, and we will not go into the detail of this integration, but what we can say is that this cos phi will be multiplied by cos phi here, and this will be cos square phi, and cos square phi can be integrated easily between 0 to 2 pi. Okay. It can it will give rise to I think pi here, it will give to pi, the solution will be pi here. However, this particular term, because of this term and cos phi, okay, over the 0 to 2 pi, this will get completely cancelled. So, we will not have any term from contribution from this part. So, we will have only this. So, therefore, what we will have is that at the horizontal displacement at any location, okay, on this area at which load, okay, will be radial, and it will go very radially, okay, increase radially, okay, from the point of application of the from the center. So, this is by the way within r within r less than equal to a, that is within the contact area, okay, within the contact. So, both V and U that we found out so far is within the loaded area. Now, let us say that we are interested in finding out the displacement at a point B which is away from the loaded area. The distance r b from the center here is r, let us say, and here this point. So, here because of this load over this whole area, okay, what is the vertical displacement, horizontal displacement here, that is what we want to find out, and that can also be found out very similar to what we did in the case in which the B was inside the loaded area. So, over here for example, the B is a point from which let us say this is a kind of center here, and this distance at an infinitesimal area is C here, and which has got the distance S, and this angle is phi. So, here you see that S varies from this S1 to S2, and this phi will vary between these two tangents, this tangent over here, this tangent here, and this tangent over here, this tangent, sorry about that, tangent over here. So, these are symmetric. So, it will go from, let us say, minus phi 1 to plus phi 1. This is, let us say, minus phi 1 to here it is plus. So, that is the way the phi will vary, and S will vary from S1 to S2, and that will cover the basically the whole area. So, we need to find out for a given phi what is the value of this S1 and S2, and that we can find out. So, for example, we can find it out by writing that S square is equal to, this is r minus S cos phi whole square plus S sin phi whole square. So, it will be equal to, that will give rise to r square minus S square minus 2 r S cos phi, and S cos square phi by S sin square phi is equal to sin square phi plus sin square phi, and this is equal to 0. So, this is the quadratic equation with respect to S, and we can solve this very easily. So, S will be equal to 2 r cos phi plus minus b square minus 4 S. So, it is 4 r square, and this is cos square phi minus 4, and this is r square minus a square. So, it is r square minus a square by this 2 here. So, it will come out to be r cos phi plus minus square root, and this is will be a square minus r square sin square phi like this. So, this is the will be the distance, okay, from this will be the this S and 1 and 2, okay, and we can find out that distance, the gap between S2 minus S1, we can find out from this relation. So, it is like that, and so S2 minus S1 will be square root of 2 into S square minus r square sin square phi square root, that we can get easily. And here remember that p is constant over here. So, p comes out of the integration sign over here. So, it is p is equal to p0 as I said earlier. So, here it is S1 to S2. So, it is S2 minus S1. So, that has to be replaced by this quantity, and so finally, we will have here S2 minus S1, yeah. So, we will have this quantity over here. So, it is, I can write it easily. So, this is 1 minus sigma square by pi e, and here it is p0 and 2, and let us integrate between minus phi 1 to plus phi 1, and this is square root of a square minus r square sin square phi and d phi like this. So, it is like this. Now, you see that in the case in which the point B was inside, we had gotten this elliptic integral of the second kind, where this phi varied from 0 to pi by 2, and that was the complete elliptic integral. So, here also we will like to get something like that, because we can then because as I said that this kind of integral does not have any analytical solution. So, it is like this. So, we have to get something like this. So, means that we have to see if we can get this integration between 0 to pi by 2. Now, that is not very difficult to see what exactly that quantity will be. So, for example, that this is phi here, and I can think of a point here like this, this here. So, we can actually think of that, okay, this angle, okay, this particular angle is perpendicular, this line is perpendicular to this particular line going from B through this point S1 and S2. So, here we can write, if you see, we can actually write, let us say S r sin, so r is this line, this point, r is this distance, right. So, r sin phi is this angle, this line. So, this is r sin phi, this is equal to this is a, and let us say this angle is lambda. So, this angle is lambda. So, let us say this a sin lambda, a sin lambda. So, you see this is interesting here, that when this angle phi goes to phi 1, so that means this point will go to here, and so therefore, this will go to here, and this is tangent. So, this angle is actually pi by 2. Okay. So, this angle will become pi by 2 here, right, and here for this point will be minus pi by 2. So, we have it, we have this transformation now, that we will do it, I will write it here, that r sin phi, sin phi, this will be equal to, let us say a sin lambda, and therefore, I will have this v at z is equal to 0 is equal to 1 minus sigma square by pi e here, and then p 0 into a into 2 and then integration, let us say from minus pi by 2 to plus pi by 2. So, let us write it doubly because it is symmetric. So, let us say 0 to pi by 2 and multiplied by 2 here, this is multiplied by 2 here, and then it will write it as, now it is 1 minus, and you see here that instead of writing r square sin square phi, r square sin square phi will be a square sin square lambda. So, it will be r square sin square phi will be a square sin square lambda. So, just 1 minute, let me just see what is here, yeah, and finally we will get yeah. So, okay, so we have to get here d phi also, right, d phi also you need to get, yeah. So, it will be a square sin square lambda divided by a square here into d phi. So, d phi will be r, sorry about that, r phi cos phi d phi is equal to a cos lambda d lambda, and so it will be, so we need to write down sin phi cos phi in terms of this r and a over and sin lambda over here. So, we need to do all that substitution over here, and one can actually do all that, and one can get here finally something like this quantity. So, it will easily come once you just write down all that substitution with d phi as a function of d lambda and other quantities. So, if you change these variables and all that, we will get here 4 here because we have multiplied by 2 from, we are integrating from between 0 to pi by 2. So, this particular integral, okay, in which we have got this a square with cos square lambda, and by this quantity, now this can be further written. So, this has to be further written as, let us say 1 minus sigma square by pi e and 4 this is pi 0. Okay. So, this can come outside the integral sign, this is a square by r, and cos square, a square by, actually we will write it here a square by r square. So, here it will be, here I will write it as, let us say p 0 into r, and here I will write here 0 to pi by 2, and this is a square by r square. So, a square by r square cos square lambda. So, that means it will be 1 minus sin square lambda. So, a square by r square into 1 minus sin square lambda divided by, it is 1 minus a square by r square sin square lambda, and this is square root of half into d lambda. So, like that we will get, and this quantity can be further expanded, okay, and you can do that, and I am not going through the whole detail, but it can be written as something like this. It can be written something like this, and so here you see that you get this term, this is one elliptic integral, this is actually another elliptic integral, and here this particular quantity, that is inverse, that is 1 by square root of 1 minus a square by r square sin square lambda, okay, square root. So, this quantity is called the complete elliptic integral of the first kind, okay, represented by capital K, and this also has values at definite values at 0, pi by 2 and blah blah, and this quantity is actually called complete elliptic integral of the second kind, that we have already seen. So, the displacement, vertical displacement at a point A, at a point B, that is away from the area of loading, okay, will be given by this quantity, So, yeah, it is like that, and the tangential displacement, again we can find out, that we have to find out, and we can be we can find it out as something like this, the same way that we did it in the last time. So, you have to take the cos function, all that, and then you have to do the integration and all that. So, here as you can see, the tangential displacement outside the loaded area is the same as though the whole load is concentrated at the center of the circle, because it is just 1 by r functionality. So, u depends upon varies as inverse of radial distance from the center. So, here as if the whole load is concentrated at a particular point, that is the center. Okay. So, that is the way this tangential displacement at B, which is actually outside the loaded area, that is R greater than A. So, that is the way we need to find out. So far it was uniform loading, but let us say the pressure distribution is somewhat different now. So, let us say that it goes something like this. So, P 0 divided by 1 minus T square by A square square root. So, how do you find out the total the vertical displacement within and outside the loaded area? That is the thing. So, in order to do that, so remember the T is the distance of this infinitesimal point from the center. Okay. So, this is the P, so that basically that. So, R is replaced by T here basically. So, what it means is that what will be the how exactly we can write in terms of S, right, that is the thing here, because we are finding out the vertical displacement at this point of B, which is at a distance S from this point of application of the load, infinitesimal load, that is at C through a small area, that is given as S d phi into ds. Now, so we want to express this T in terms of this S and of course R and cos phi. So, that can be easily done. So, here for example, T square, this T square is equal to this length square plus this square, that is basically that. So, this quantity is R plus S cos phi whole square plus S sin phi whole square. So, it is like this therefore, and if we expand it, it will be like that. So, over here P as a function of S and phi can be written as very easily as this. So, remember that is inverse over here. So, therefore, this when A is taken out, it will be P 0, it will be P 0 into A, and it is like this. Now it is the same thing as we did it in the last case, that is with uniform load. So, we will replace this V here by this quantity. So, it will be 1 minus sigma 2 pi mu, and here let us say the phi varies from 0 to pi, and therefore, S will vary from 0 to S1. So, let us say it is 0 to phi 0 to pi sorry 0 to pi here, 0 to pi here, 0 to pi here, and it will be P 0. So, S is varying from 0 to S1 here, and this is P 0 into A, and this S square minus R square minus 2 R S cos phi minus S square and 1 to the power minus 1 2 1 by half, and then it is ds, and then it is integration with respect to d phi. It is like this. So, we have to find out the integration over here, that is one we need to find out, and of course, we need to find out S1 also. So, S1 is basically same as what we had found out in the last time. So, for S1 varies from 0 to S1, so phi has to vary from 0 to 2 pi. So, I should write it as 0 to 2 pi, because it is S is varying from 0 to S1. So, a phi is actually varying from 0 to 2 pi, not pi, it is 2 pi here, right. So, like that. Now, we need to find out this integration now with these limits, and that is what is written here. And how to do that? Estimated is already done. So, that is this quantity, because we have already done it in the same way as before. So, over here what we have is, let us say I have something like this, that this is 1 by square root of S square minus R square minus 2 R S cos phi minus S square into ds, and here we can write this particular term as something like this, 1 by let us say we write it as S square minus R square sin square phi S square minus R square sin square phi minus, here I write it as R square cos square phi minus plus, this is 2 R S cos phi and plus S square bracket square root, and it is ds over here. So, see this term is R cos phi plus S square, and this time. So, it is kind of it is in the form of square root of 1 by square root of a square minus x square, and dx, let us say, in this form. So, we know that the solution, the integration of this quantity comes out to be sin inverse x by a, like that. So, here I will have actually sin inverse, and this x instead of x I have r cos phi plus x, this is r cos phi plus s, and for a I have this quantity, that is square root of a square minus r square and sin square phi, like this. And this varies from 0 to S1, remember that it varies from 0 to S1. So, here I have like this. So, now 0 to S1. So, S1 I can substitute whatever is the value here. So, you can see here S1 plus cos phi is given by S1 plus r cos phi will be this quantity, which is over here, and then instead of s here it is 0 here. So, this is this quantity. So, here this can be, this one is actually replaced by square root of. So, it is square root of this quantity, okay, can be written as, this can be written as square root of a square minus r square sin square phi square root, okay, and so therefore, this is actually equal to 1. So, therefore, it is actually equal to pi by 2 minus. Now, this quantity I can do it little bit differently now. I can write, we can actually obtain this quantity, what it will be, and we will show that this quantity, okay, when we integrate it with respect to 0 to 2 pi, that will be equal to 0. So, for example, let me write it that the sin theta is equal to this quantity r cos phi by a square minus r sin square phi, and so then it is cos theta is 1 minus sin square theta, and if I find out that, so it will be cos theta will come out to be like this. So, tan theta will be like this. So, tan theta, okay, will be r cos phi square root of a square minus r square, from which theta can be obtained like this. So, I started with this quantity sin inverse this, and this can be replaced by tan inverse, this is r cos phi, tan inverse r cos phi by square root of, this is advantageous, r cos phi square root of a square minus r square. So, here you see the phi dependence is only through cos phi, and therefore, this is when you are integrate, when we integrate with respect to 0 to 2 pi, this term will fall out. So, we will only have pi by 2. So, therefore, I will have here this is equal to 1 minus sigma square by pi e, and this is p 0 into a, and it is 0 to 2 pi, this is pi by 2 into d phi over here, and so therefore, it will come out to be 1 minus sigma square by pi e p 0 a, this is pi by 2 into 2 pi. So, 2 gets cancelled here, this pi gets cancelled here. So, I get here 1 minus sigma square by e, and this is e, this is p 0 a and pi, like this. I hope I did it correct, pi into 1 minus sigma 0 e p 0 a, like that. So, P 0 is the load power unit area. So, I can also find out what will be the total load that is applied. So, that can be obtained from this integration. Remember that. So, this defines the load that is applied on a thin strip, not on thin strip, on a ring with the radius dt, and so it can be found out like that. So, this integration. So, basically this is the whole area. So, applied load is applied, but I can consider a thin ring over here with radius, let us say t, and then this thickness of this ring as dt. So, the load is applied whole through this area, that is this quantity, and then we integrate from 0 to a, and that will give rise to this value 2 pi a square, and so p 0 will be equal to a capital P by 2 pi a square, and instead of p 0 I will write 2 p by 2 pi a square. So, finally, I will get this expression. So, this is the expression, and what is interesting here, you see that we are trying to find out the displacement or deformation at a point r, radius r, okay, from the center, and that comes out to be independent of r. Okay. So, what it means that when we have this load distribution P0 into 1 minus r square by a square minus 1 by 2, okay, this kind of load distribution will lead to this kind of uniform deformation at the surface. So, basically in essence what it means is that it is possibly a circular flat plate punch, okay, which is pressed against this this elastic half space. So, it is like that. So, it is a constant vertical displacement whole through the area, that is why it gives rise to. Now, let us say we are interested in figuring out that what will be the displacement, okay, in these polar regions, let us say in a point that is outside this contact area. So, we need to find out that. So, we will find it out again by writing like this. So, here this is the point B which lies away from the center, and the same way as before for this uniform load that I did, okay, we will figure it out. So, again that T can be replaced, okay, T has to be replaced by A with respect to T has to be written with respect to in terms of S and phi, and that we can easily do. So, over here I have already done it in the, I am not repeating that once again over here, and we will get something like this here. So, now as you can see for a given phi, S varies from S1 to S2, okay. So, we have to find out what will be the value of S1 and S2, that we can do, and the phi will vary from minus phi 1 to plus phi 1. So, that is the way it will vary. So, here S1 2 are the roots of this particular equation. So, S square, so S square will be equal to S square. So, basically S12, so let us say this point, and this is, let us say this is the perpendicular and this is the line radial distance here. So, this distance is S square. So, this is A here. So, S square will be equal to, S square will be equal to what? Will be equal to R, this is R and this is S, R minus S cos phi, okay, square plus S sin phi whole square. So, this is equal to R square minus S square minus 2 R S cos phi, okay, plus minus plus S square, okay, is equal to 0. So, if I find out the solution of this equation for S, I will get this point S1 and S2. So, that can be obtained easily. So, these are the solutions of this point of this equation R cos phi plus minus square root of S square minus R square sin phi, and we can use these values of S1 and S2. So, here the integration will be, we have to do this integration over here from S1 to S2, and here that comes out to be like this. So, here once again when you write it, substitute for S1 and S2, let us say S2 and S1. So, when you substitute that this expression for S1 to S2, it will say you will get pi by 2 here and minus pi by 2 here. So, the minus pi by 2 plus pi by 2, it will come out to be pi. So, it comes out quite nicely, and then we can substitute over here. So, we will get here for this part, we will get here pi, here pi I have gotten, okay, and then we will get pi here, and then we will get here phi. So, the phi varies from minus phi 1 to phi plus phi 1, and the phi here is, what is the phi here? Here it is this phi 1, this phi 1. Phi 1 is equal to sine inverse, okay. So, phi 1 is basically this angle. So, here is the sine inverse. So, this angle will be this sine inverse A by R. So, this is the perpendicular. So, yeah, so it is A by R, right, the sine inverse A by R, and so therefore, over here I have directly written here. So, phi when you integrate it, d phi, it will be 2 phi 1. So, it is 2 into sine inverse A by R. So, finally, you will get this expression. So, what it means is that in this region, okay, in this region, this is basically a sine inverse function. So, if you want to know how does a sine inverse function look like and practically obtain it, this is the way that you have a flat punch, press it against an elastic half space, and then find out the deformation, vertical deformation outside the loaded area, and you have the sine inverse function, right, like that. Now, we can also obtain the of the gradient of the deformation, and that will be something like this, and we can easily show that at r tends to a, for example over here, so you will get here 1 minus s square by r square. So, you will get here del v by del r is equal to infinity. So, del v by del r being infinity means that this is the gradient is infinity there, and so it is a very sharp corner, that is because of the sharp corner of this indenter that presses against it. So, today I will stop here, and in the next lecture I will take up the horizontal displacement, also we will take up some another particular stress profile or loading profile, okay, on this particular elastic half space. So, thank you for your kind attention.